We've talked about how we understand events as being sets, and in particular them being subsets within a sample space, omega. So I think it would be useful to, here in this subsection 2.3, to talk a little bit about some set theory. We're not going to go super deep into set theory. There are other modules at the university where you'll have the opportunity to do that. Just a few basics that are going to help us out. So the first thing I want to start with is if you have an event or a couple of events, you can build new events out of these in some simple ways. We're going to start by talking about those. So the first one I want to talk about is not. That is, if you have an event, you can also have not that event. So here in this first square and circle on the right, the square on the outside here is representing omega, the entire sample space, and this circle in the middle is representing a particular event, A. And so if we think of that circle and everything inside being an event A, then the event that A doesn't happen is everything that's in the sample space but is not that set A. So that's all of this. Right. This area here, the part of the sample space that isn't in A, which is not A, and the letter we use for that is A with a little c at the top, and we call it a complement. So let's just write that down. The complement of A, and when we say this out loud, we either say a complement or we just say not A. A with a little c up in the air is the set of sample points not in A. Okay, excellent. We can continue on with the next picture down. Again here, the square on the outside is representing omega, the entire sample space. And here we've got two events. The circle on the left, including the overlap bit, is A. The circle on the right, including the overlap, is B. Of course, there's the bit in the overlap. That's the set of things in both A and B, right? So if we call this and, then this bit here in the middle, stuff that's in A and B, which we write as A, and this kind of curvy upside down U letter, B, which is called the intersection. So let's write that down as well. So the first one was the complement, the second one is the intersection of A and B, which we write as A, that kind of upside down U thing, B, is the set of sample points in both A and B. And so this represents the event that A happens and B happens. We say either A intersect B if we want to be fancy, or A and B if we're happy with being non-fancy, that one. Finally, you might be able to guess what's coming next. It's an OR. So again, we have a sample space A, we have two events A and B, and OR is the event that A happens or B happens or both. And so that's the set of sample points in A or in B or in both. So we have the ones just in A, we have the ones in both A and B, and we have the ones just in B. It's called an inclusive OR. In mathematics, ORs are always inclusive, and so they allow both. This one is A or B with a proper way round letter U here. And the formal name for this is the union. So a union of A and B, which is A or B, the set of sample points in A or B, which
includes
both. So those are our kind of three ways of getting new events from old. We've got given an event, it cannot happen, which is a complement. Two events A and B can both happen, which is the intersection. Or at least one of A and B can happen, which is the union. So I am not ashamed to say that I learned about unions and intersections more than half of my life ago, and yet I still remember which way round the symbols are, because the one for intersection looks a little bit like a lowercase n, which is a letter in intersection, and is also a letter in and I'm also not ashamed to say I remember the symbol for union, because it's that, which looks like a lowercase u, which is the first letter of union. And if you say or in a really funny voice, like kind of or, you can kind of make it sound like it starts with the letter u. And so that is still how I remember which way round the intersection and union signs are. If you can actually remember it properly, then good for you. This is how I remember it. I guess it would be good just to see an example of how these work, just to check that we really understand what the definition of this not complement and intersection or union are. So my example is this. Pretend we're rolling a dice again. We saw that example previously. So here our sample space omega, the set of numbers from 1 to 6, representing what number we get on the roll. And let's give ourselves some events here that we can work with. The first event will be the event that we roll an even number, which of course means that we get a 2, a 4, or a 6. And our second event will be the event that we roll at least 5, which of course means that we have to roll 5 or 6. So let's do a complement and not. What's a complement? So a complement is all the numbers in omega, 1, 2, 3, 4, 5, 6, apart from the ones that are in A, which are 2, 4, and 6. So that leaves us 1, 3, and 5. Those are the sample points that are not in A. And of course, you can see that that's equivalent to rolling an odd number. So the event that you don't roll an even number is the event that you roll an odd number. I think that's fairly clear. What about A intersect B? That's A and B. So that's the set of sample points that are in the event A and are in the event B. Well, let's just look at the two lists. A is 2, 4, 6. B is 5 and 6. So there's only one sample point in both of those, and that's the number 6. So the event A and B, or A intersect B, is the event that we roll a 6. What about A union B? So A union B is all the sample points that are in A or that are in B, and we include that are in both in that. So that's the 2, 4, 6 from A and the 5, 6 from B. Happens that we have 6 twice, but no need to write it down twice. Things in A or B are 2, 4, 5, and 6. I can't think of a snappy name for that set. It's just the set of 2, 4, 5, and 6. So that's an example of how this not complement and intersection or union work in practice. There's an important special case that will come up both later in this section and at various other points later in the module. And that's when two events can't happen at the same time. If two events can't happen at the same time, well, before I write the consequence of that, let's just think, how would we write that in mathematics? That would say that there's nothing in their intersection. Right, so A and B, well, they can't happen at the same time, so there's no sample points in that. You might remember that we used this O with a line through it for the set that doesn't have anything in it. So if they can't happen at the same time, that means there's no sample points in their intersection, because the intersection represents and. Then A and B are called disjoint. They're disjoint events because they can't happen at the same time. Another phrase for this, which is just more syllables for the same thing, is mutually exclusive. I normally just say disjoint because it's a lot fewer syllables, but disjoint or mutually exclusive means they can't happen at the same time. And that will be useful in various places, because events that can't happen at the same time are somehow easier to deal with than events that do have an overlap. So, for example, like in a deck of cards, the card is a spade and the card is red. A disjoint events because the spades are all black cards. The red cards are not black, and so you can't have both a spade and a red card. So they're disjoint or mutually exclusive, and somehow that's more convenient to deal with. So there are some rules about how these unions, intersections, and complements go together. And I'm almost not sure whether I should show you them or not, because I think whenever we use some rules about how these interact in these courses, it'll probably be so obvious that you'll just know it without me writing down and confusing things. On the other hand, we're at university now, why not do a little bit of set theory? So I have written these rules down, but I can't honestly recommend that you say memorize these or something. So just here is what I wrote down in the notes. So the first rule is the double complement rule, that not A is the same as A. Right, that's the thing you know. If it's not raining, then it's raining. Two negatives make a positive. So I felt that somehow I'm slightly making it even more complicated than it already is just by writing it down, but there we go. We also have these distributive laws about multiplying out of brackets. You might compare these with what you know for like just normal numbers. You know that A times B plus C is equal to A times B plus A times C. And these are like the equivalent for sets. You can multiply out of brackets the same way. And De Morgan's laws tell us how we how we combine intersection and union with complement. So like I say in the text just below, this A and B complement equals A complement or B complement. That sounds like an incredibly complicated statement. But if we phrase it as if it's not a Monday, if it's not a Monday in October, then it's either not a Monday or it's not October. Right? Then it kind of seems so obvious that I kind of wasted effort by writing it down. Similarly, if this maths video is not useful or fun, then it's not useful and it's not fun. I mean, again, I wrote it down because we're doing maths at university now and I felt like I ought to. I wouldn't want you to fret too much about these kind of fairly common sense statements. However, it's perhaps good to be able to prove statements about sets. So I did want to do that. And there are kind of two ways that you can prove statements about sets. One is that you can, if you've got an equality, you can draw a Venn diagram for this side, you can draw a Venn diagram for this side, and you can see whether the Venn diagrams are the same. The computer draws much neater Venn diagrams than I can by hand, so I put an example of that in the notes. You'll see the bit of the notes that has all the pictures of Venn diagrams in. And I think I'm just going to point you to that rather than try and draw Venn diagrams on my iPad down here, which would just be messy. The other way you can do it is by doing a truth table. I do want to do that on video here because I think it's more easy to see on the video than in the text. So I'm going to try and prove the first of these De Morgan's laws, which is that A and B doesn't happen, and A doesn't happen, or B doesn't happen. And so I've set myself out a table, and there are two events involved here, A and B. And so I want to look at all the different combinations of whether A is true, or A happens, or omega is in A, and all the combinations of whether B happens, or whether B is true, or whether omega is in B. So each of these can be true or false. So A could be false, and B could be false as well. A could be false, and B could be true. A could be true, and B could be false, or they could both be true. And I'm going to start with the left-hand side of this equation. A intersect B complement. I'm going to split this down into 2 bits because I don't want to do it all at once. I'll calculate A and B first, and then do A and B complement. So A and B, this is only true if both A and B are true, which is clearly the bottom column. If either one of A and B is false, then A and B is false. Okay, but that's not actually what we wanted. What we wanted is A and B complement. And so that's just the opposite of A and B. So I can take the third column and write down the opposite thing. The false becomes a true, the false becomes a true, the false becomes a true, and the true becomes a false. So that's kind of the truth column for A and B complement. I also want to do this for the right-hand side of the thing that we're trying to prove, A complement or B complement. Again, I'll split that up into bits. So I'd like to know A complement, and I'd like to know B complement. A complement is just the reverse of the A column, right? The A column was the very first column here, which was false, false, true, true. So A complement is the opposite of that, which is true, true, false, false. Similarly, B complement is the opposite of the B column. B column was the second column, which went false, true, false, true. So this will be the opposite, which will be true, false, true, false. And now I've got A complement and B complement. I can put them together to get A complement union B complement. So this is true whenever at least one of the previous 2 columns is true. So they're both true there. The A complement is true there. The B complement is true there, but neither of them are true in the bottom one. So here we've done the column for A and B complement, and we've done the column A complement or B complement, and we see that those columns are the same, right? They both go true, 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 false. And thus those 2 events are indeed the same. So that's the way that if you want to prove things using a truth table, you can prove them with a truth table. So that was just a little bit of set theory, just that might help us along a bit later. But next, we're going to really be able to look at probability, the thing that we're actually here for.